Hello, this is Brian Washburn. I'd like to do one problem in a rigid body type problem using what we learned about more sophisticated formalism of handling rigid bodies. So what I'm going to do is I'm going to look at what's called the precession of a top due to a weak force. We actually talked about this in engineering physics. You did a demo on this, and what we did in the demo is we took a bike wheel, we spun it, we hung it by a loop or a rope, and then that bike wheel kind of precessed around the axis. And so what I want to do is I want to describe that precession or get an expression that talks about the frequency of that precession. All right, so here's my kind of picture. What I have is of a bike wheel. Here's my bike wheel here, okay? And then there's a rope, and I'm going to put the origin of the coordinate system at the end of the bike wheel, so the kind of the handle. And then at the end, there's a rope that goes up, and there's a tension here associated with it. Now, what makes this really kind of difficult is it is a three-dimensional problem, so you have to really consider things. Now, by the way, the axis, we're going to keep the axis fixed because the axis is fixed. But at times t equals 0, this is what we have. All right. So now again, now we actually, again, we did exactly this problem in Engineering Physics 1. I did it in studio. But again, I'm going to do it here using this kind of more sophisticated formalism that we learned in handling, this idea of a moment inertia tensor. So a bike wheel is what I would call a symmetric top. And a symmetric top has, so again, there are three principal axes for a symmetric top. So I'm going to assume that I'm going to work with the diagonalized version of the moment inertia tensor. And a symmetric top has I1 is equal to I2, which is not equal to I3. So that's what my moment inertia is, a tensor. So I can write my tensor as a diagonalized thing. And in fact, if I choose this coordinate system at times t equals 0, I will get a diagonal matrix. So I'm just going to call this I1, I2, I3, and then 0, 0, 0, 0, 0, 0. Okay. And you can see that this thing here, I3 represents the rotation of the bike wheel, okay, about that axis. That's the moment inertia associated with that. I1 is really a rotation about the axis, about the x-axis, which I have pointing up. Okay, so really most of the rotation is along. If you want to write the angular, so initially, let's write the angular velocity as a vector. The angular velocity is going to be a vector that points like this, and that's going to be a large number pointing in the z direction. Okay, so now let's write down an expression for that. Okay, the angular momentum. It's going to look like this for the most part. Okay, and we'll explain a little bit why. So the angular momentum, angular velocity is going to be 0, 0, omega. That's because it's along the z-axis. Okay, so now how am I going to solve this problem? Well, I'm going to use basically Newton's equation. Newton's equation for torque shows that the rate of change of the angular momentum is equal to the net torque on the system. So that means the first thing I have to do is let's first calculate L. So L is the angular momentum. That's going to be equal to, well, it's going to be equal to I omega. All right. But again, I have to do this matrix multiplication business. And you can see here, well, it's really nice to have diagonalized matrices to do this. Okay, and then I get here 0, 0, omega 3. Well, that product's pretty simple. And then what I'm going to get is I'm going to get 0, 0, I 3, omega 3. And then we can write that in a kind of vector notation as I 3, omega. Oh, actually, well, omega 3 is not omega 3. We're just calling it 0, so let's just get rid of the 3 there and the 3 there. So we're just going to call that omega. Okay, in the z-hat direction. Okay, so that means the angular momentum. So as long as you choose, this is interesting, as long as you choose a principal axis system, in this case, the direction of omega, the direction of omega is going to be the same direction as L. All right. So one of my equations of motion is just is going to be equal to, well, not even an equation, but one of my most important equations, L is going to equal to I3 omega z hat. All right. Okay, now what we want to do is we want to look at the, eventually we're going to take the rate of change of that, okay? But now let's look at the torque. Okay, torque, okay, again, this is using engineering physics language. It's R cross the net force. Okay, now what forces create torque? Well, there's a tension acting on it, and there's gravity acting on the center of mass going downward. The tension doesn't create a force because the tension acts at the axis of rotation. So the tension doesn't create torque, but mass, the weight of the object does. And so what is R? R is a vector from the origin to where the force mg acts. Well, that's going to be, that R vector is going to be L z hat. R is, again, just drawing it on this little picture. Should have made this a little bigger. But big R is just a little vector that points like this. Mg is a vector that points down like that. That's Mg, like I showed there. And so I can rewrite this L cross, and then here what I have is minus Mg x hat. Okay, so that's going to give me MgL, and then z hat cross minus x hat, that gives me minus y hat. All right, okay. So that's the air equation I want. So this is one main equation here, and then here's my other main equation here, minus MgL y hat. Okay. So now let's stick that into the rate of change of L is equal to the net torque acting on the system. So I'm going to say d dt of L, okay, and let's put in L, I3 omega z, and that's going to be equal, and that's in the, sorry, it's in, yeah, that's correct, have that, and that's going to equal to minus MgL y prime. Okay, so if you take a look at that, okay, so think about what changes here. I doesn't change, the bike wheel doesn't change its shape anywhere. Omega, does omega change? Well, for a weak torque, for initially this thing here, the only thing that changes omega is really the frictional force in the bike wheel itself. Gravity doesn't change it. So this is a constant. So something's got to change. So it has to be the z hat direction. Okay. And so I guess when I said it was fixed, it wasn't technically correct. But anyhow, that's just a a word typo. So let me say, so what I have here is that I have to have that, and that's equal to MgL y hat. Okay. So from this, I can say the magnitude of the rate of change of z hat is going to be equal to MgL I 3 omega. So what's going to happen is, if we do fix the axis to the object, then the z hat direction is going to rotate with an object, and the rate of change is going to be given by that expression there. Now, let's do this. Now, what we've done is, okay, so let's take a look at that. Now, previously, when we talked about non-inertial reference frames, we talked about that if I have the rate of change of a position vector, I can always say that's equal to some angular velocity, capital omega, across the vector itself. Now, what is that going to be? That is going to be the velocity of the precession. Okay, and back to my picture, the thing precesses like this. So omega, capital omega, is going to be a velocity vector that points up like this. That's what I expect, because the whole thing precesses around like this. All right. Okay, so let's calculate that. Okay, how am I going to do that? Well, basically, I'm going to rewrite this thing here in this form here. Okay, so going back to what I had before, basically this equation here, I can write I3 omega, and then I have dz hat dt, and that's going to be equal to, and then actually what I'm going to do is instead of writing, I'm going to use this term here. Okay, and you'll see why in a minute, because, well, the reason why I'm going to use that term is because there's a z hat term there, and that's important. So instead of computing the cross product, I'm going to write out the step before, minus mgx hat. Okay, so let's factor out all that. So I'm going to solve for dz hat dt. Okay, and I'm going to factor out a bunch of constants in front. I'm going to get minus mgl, and then I have I3 omega. And then here I'm going to get z hat from here cross x hat. That's what I have. Okay, so everything's fine there. Now what I'm going to do is I'm going to basically flip, use the anti-commutative property of the cross product, and I can write this. Again, what I'm trying to do is write this derivative in the form of this thing here. So if I do that, I'm going to get mgl I3 omega. Then I'm going to get x hat cross z hat. Well, I'm there. So now what I can do is I can rewrite this sucker as omega cross z hat, where that thing there is equal to mgl I3 omega. Okay, in the x hat direction. So what is this thing here? That is the angular velocity of the precession. It depends on all that stuff, and it points in the positive z hat direction, and that's exactly where I pointed it, say here. Okay, so that's my precession speed, and that's the precession speeds for a pendulum. I'm sorry, for a gyro or bike wheel or something like that. Okay. Now I'm going to actually do an example. I'm going to bring in a little gyro, and we're actually going to look at the precession and actually calculate the precession. But there's actually a cool thing about the precession, and you notice that capital omega is inversely, so the magnitude of the capital omega is inversely proportional to omega itself. All right, that seems very counterintuitive. All right, but actually you see this with a gyro all the time. So if you ever take a gyro, get one of these toy gyros, and we'll bring one in class. You get it going, and then eventually little omega is the the initial angular velocity of the thing. Okay, but eventually the thing is going to slow down because of the bearing. There's some friction in the bearing, and then what happens? You say you point this thing up, initially. So what you do? So you take a gyro, and say you point in this direction, and you spin it like this. So omega is like this, and then it precesses about some axis like this or something like that. So it goes around and around and around like that. Now, as omega slows, one thing you'll notice is we notice that this thing here, as omega slows, this thing here will tilt more toward the ground, okay? But then this gets smaller. But then this thing here, it precesses actually faster. In fact, when it's just about to fall, it's really whipping around pretty. Omega is very large. Capital omega is very large. Well, that's because of this inverse relationship between as little omega slows, big omega should get bigger and bigger and bigger. Okay, and we'll observe that in class. I bet you've seen that with a gyro. And if you haven't, go out, buy a gyro. Every physics student should have at least 1 or 2 gyroscopes. All right, I got 3. Maybe I have 4. I don't even know. But you should go buy one. All right. If you need a loan, I'll give you a loan maybe, but I don't know. But anyhow, go buy one. It's $8. Okay. All right. So that's a precession of a top under a weak force. We're going to do much more complicated problems, but not right here. Okay. Take care. Bye bye.